Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is another lecture for intermediate algebra focused on quadratic inequalities, and this is the part C of that lecture series. In this lecture, we're going to focus on solving quadratic inequalities using algebra rather than graphing. First thing we need to do really is just to define what a sign chart is. This will be the one object we'll be able to use to help us graph quadratic inequalities, or solve quadratic inequalities. And it's really the only thing you need to use aside from being able to solve quadratic equations. The best way to understand what a sign chart is to actually solve a quadratic inequality. But we'll start with something extremely simple. And actually, perhaps I should write down, or actually just have, the idea of what we would do to solve an inequality, and that actually gives us the idea of what a sign chart is. To solve an inequality, first we rewrite the inequality in the form stuff is greater than 0, or stuff is less than 0, or stuff is greater than or equal to 0, or that junk is less than or equal to 0. It doesn't really matter. It's just get 0 on one side, everything else on the other. At that point, you're essentially asking yourself, when is this stuff bigger than 0 or less than 0? And the better question to ask initially is, well, let's just find out when that stuff is actually equal to 0. It's an important step. Once you find those solutions when it equals 0, let's say that's at x equals 2 and x equals 5, you plot those 2 points on, or 3 or 5 points, or whatever it may be, on a number line, and then you pick test points in the resulting regions and plug those into your equation, your junk equation, to see what the resulting sign is and write those signs above those corresponding regions on the number line. Now, that seems like a huge bitter pill to swallow. So and I'm also not a huge fan of memorization, but this is one of those things that you almost have to get used to until you don't feel like you're memorizing it, and instead you feel like, you know what, it just makes sense that you're working it this way. So let's see this in action by looking at a quadratic inequality that we just dealt with in a previous lecture. We actually graphed this in the last lecture. This time around, instead of graphing it, we're going to solve this algebraically. Now, let's try to take a very common sense approach to this so it doesn't use too much memorization. Instead, just think about what you need to do. If you look at this is something completely foreign to you at this point. You're a little more intimidated. I mean, if there was an equal sign there, it would be much better for you. But because there's no equal sign, you get very intimidated by that. So what you can do is you could change it to an equal sign in the meantime. So in other words, you could change it. But before we do, let me rewrite as 3x squared plus 6x plus 1, and then I'll subtract 4 from both sides. In fact, let me go ahead and write that subtraction in. Oops, let me subtract a 4 here and subtract 4 there. And if I do that, I get the following. 3x squared plus 6x minus 3 is greater than or equal to 0. And now I will say, you know what? I know that I could solve this quadratic if it were an equation. So let me go ahead and rewrite that as an equation. So I'll do this in a different color. I'll say that's like 3x squared plus 6x minus 3. Let's solve this equation first. Remember, when you're solving a quadratic equation, you want to factor out what everything has in common. So each of these terms has a 3 in common. I'll pull that out. X squared plus 2x plus 1. Or, I'm sorry, not a plus 1. That's a minus 1. And that's all equal to 0. And now I could try to factor that quadratic in there to continue solving, and it might factor, but it doesn't. That doesn't factor. So before I continue, I'll note, if I'm going to solve this equation, I could actually divide both sides by any number I want that's non-zero. I'll divide both sides right now by the number 3. The reason why is it just makes my life a little bit easier, because I can see 3 over 3 is just 1. So that's actually going to turn into a 1 times all this stuff. Or in other words, x squared plus 2x minus 1 is equal to 0 over 3 is just 0. So again, I started with a quadratic inequality. I didn't know what to do, but I thought, well, first thing I could probably do is just move everything to one side. Anything with a quadratic usually works that way. You move everything to one side. And then I don't know how to solve this, but I know how to solve an equation that looks like that, so I'll do that instead. And I get to this point and I cannot factor it, so I'm going to use a quadratic formula here. Quadratic formula says take the opposite of the b term plus or minus the square root of that b term squared minus 4 times the a term times the c term. I keep saying term when I say that stuff, and it's really not term. It's a, b, and c. I shouldn't say the word term, but I am, so oh well. And this simplifies down quite a bit. It's just x equals a negative 2 plus or minus the square root of 4 plus 4, which is 8, all over 2. And actually, this even simplifies down a little bit more, right? Because 8, right there, can be rewritten as 4 times 2. I happen to know the square root of 4. I don't know the square root of 2. So this can be written as negative 2 plus or minus square root of 4 times the square root of 2. I'm doing this kind of slowly, which is equal to negative 2 plus or minus 2 times the square root of 2, all over 2. I might as well just continue out here. Both the terms in the numerator share a number in common, the number 2. I'll factor that out front. I'm left with a negative 1 plus or minus the square root of 2, all over 2. And 2 over 2, those are common factors we can cancel to turn into the number 1. So this will just be a negative 1 plus or minus the square root of 2. What a mess that is. Now normally when you're given an inequality in one variable, you generally want to graph that anyway. So what I'm going to do, and by the way, what I mean by that is if you're given something like, let's say x is greater than 3, or something like that, or 3x is greater than 3. When you solve that, you're going to want to graph that on a number line. And that way you could shade and kind of get an idea of what it looks like. Let me erase that now. So in our case right here, I'll go ahead and create a number line. And on this number line, I'll put the number 0, actually. And then I'll put negative 1. And the only reason why I put in negative 1 is because normally you wouldn't have to, but I'm actually going to be at a negative 1 minus a root 2 and a negative 1 plus a root 2. In fact, maybe for this example, I'll even just take those out of here. Maybe that would be a little bit much for people. So let me just take that out and instead just grab a calculator to show you what negative 1 plus a root 2 is and what a negative 1 minus root 2 is. So here's my handy dandy graphing calculator. And I'll just say negative 1 plus the square root of 2. And that's going to turn into that number right there. And a negative 1 minus the square root of 2. Turn into that fancy number right there. So I have two numbers I'm going to plot on this page. A negative 2.4, and I'm just going to say roughly negative 2.4. And then the other one, I'll have roughly a 0.4. Very roughly a 0.4. I'm doing very harsh rounding here. So, okay, so I know that these are two very important points on my, get out of that. I know those are two very important points because they're solutions to my quadratic equation. But unfortunately, this is not a quadratic equation, it's a quadratic inequality. And I want to know not when this quadratic equation is equal to 0, I want to know when it's not only equal, but when it's greater than 0. In other words, positive. So when is 3x squared plus 6x minus 3 positive? Well, now we know when it's 0. So if it's 0 at negative 2.4 roughly, and if it's 0 at 0.4, again roughly, then everywhere else it's either positive or negative. So what I'll do is I'll start over here in this region on the far left and just pick any point I want. And a good point to plug in maybe is like x equals a negative 3. If you plug in an x equals a negative 3 into your quadratic inequality here, you can determine whether it's positive or negative. So let's do that. So 3 times a negative 3 being squared, well, that's 9 times 3, which is 27. Minus 18 minus 3. Now that's still positive. Okay, so in this area right here, I know it's positive. Now let's pick any number between negative 2.4 and positive 0.4, and a great number to pick is 0. So if you plug 0 into your quadratic inequality or your quadratic equation, however you want to call it, you'll get that it's equal to negative 3, which is definitely less than 0. So it's negative in this region. And when I say negative in this region, I mean this entire interval from negative 2.4 to positive 0.4, it is going to be a negative value. Your quadratic equation is, that is. And now we go ahead and pick something beyond 0.4. Let's try x equals 1 because, well, that's an easy number to pick. So I plug in 1 in here. And when I do that, I see I get 3 plus 6 minus 3. And I know that that's going to be greater than 0. I mean, you can easily see that that's going to be a number greater than 0. So it's positive in that region. So let me highlight the regions where it's positive, because that's really what we want to know. When is this positive? All throughout here and on forever, and all throughout here, and again on forever. And because we want to be equal to 0 as well, we don't mind including those edges. We don't mind including this edge right here or including that edge right there, because the fact is we want to know when we're greater than or possibly even equal to 0, and we're equal to 0 at those points. So the solution to this quadratic inequality is going to be everything from negative infinity all the way up to about negative 2.4. Remember, that's a rough estimation, including that number. And union that with everything starting at 0.4 and moving on to infinity. Now, to be honest with you, this is not a style of answer that I would like to accept. I actually don't like this answer at all, because once somebody grabs a calculator, they're kind of wrong. So instead, if I were you, I would highly recommend sticking with these exact numbers. In other words, I would recommend writing my interval going from negative infinity all the way up to negative 1 minus a root 2, and then unioning that to the interval starting at negative 1 plus a root 2 and continuing on to infinity. Right? Because this is negative 1 plus root 2, and this is a negative 1 minus root 2. So let's go ahead and try this technique again, just to get used to it. Let's solve a quadratic inequality where we have to start kind of moving things over first. So whenever I see anything that involves squares and basically two different versions of my variable, I know immediately that I'm going to have to move everything to one side. I have to use special techniques to solve something like this, which either means factoring or the quadratic formula. Let's go ahead and move everything to the left. I'll add 2x squared to both sides and subtract 2 from both sides. And I get this beautiful 6x squared plus that x is just sitting there minus 2 must be greater than or possibly equal to 0. Now I'll quickly try to factor this if I can. It'd be great if I could. So let me try. Let's see. 2x and a 3x. Those two numbers multiply to a 6x squared. That works out. And this could be a 2 and a 1. Let's see if that works. That's a 4 and a 3. Oh, that works perfectly. So I'll put the 2 here and the 1 there. I'll erase the ones below. And we just have to figure out the signs in those. Well, if it's a positive 2, then we have 2x times 2, which is a 4x. It's a negative 1. We have a 3x times the negative 1, which is negative 3x. So 4x minus 3x, that's an x. Negative 1 times 2, that's a negative 2. Perfect. This is beautiful. This example might end up looking a little bit easier to you. Now, once I get it factored, I'm thinking to myself, well, I don't know how to solve something like this. Instead, I know how to solve the equality. So let's go ahead and solve 2x minus 1 times 3x plus 2 is equal to 0. And that's easy because we've already factored it. It just implies that x is equal to 1/2 or x is equal to a negative 2/3. So that's when this quadratic inequality actually turns into 0, is at these 2 points. Let's go ahead and graph a line and plot these 2 points on it. So let's see, 1/2, we'll just plot right there. A negative 2/3, we'll just plot right there. I know there's a point in between them, 0, right? Okay, so we've plotted our 2 points. At these 2 points, we're equal to 0. So in other words, I want to include these 2 points in my solution. Now let's see when we are actually positive, because that's what this is asking, when are we positive? Not always it's just these last 2 examples that we're asking that our quadratic equation be positive. But you have to be careful, because sometimes they might be asking, when is it negative? Okay, well, you do the same process. It's just when you plug in points, you're looking for the regions where the outputs are negative. Let's choose good values for test points here. I think in this region an x equals a negative 1 is perfect, because that's below negative 2/3. In this region an x equals 0 is perfect, and in this region an x equals 1 is beautiful as well. So let's go ahead and plug x equals negative 1 into our quadratic equation. If you do that, I personally, when I do this, I've always gone to the factored version of it, but a lot of students hate that, so I'll just do this. If you look at that, that's a positive 6 minus 3, so that's still positive right there. If we were to plug in x equals 0, we would get a negative 2, which is a negative number. And if we were to plug in x equals 1, well, you can see what's going to happen. It's pretty obvious. That's going to be 7 minus 2. It's positive. So I have the regions where we're positive, where our quadratic inequality is positive. So let's go ahead and shade those regions, because that's really what we're interested in, is when it's positive. That would be this region right here. And I'll draw the little arrow at the end. And this region right here. And again, I shall draw the little arrow at the end. And because we want to include these endpoints, we'll go ahead and put these little brackets here. Therefore, our solution set is the interval, negative infinity, all the way up to negative 2/3, and including negative 2/3, unioned with everything starting at 1/2 and climbing on to infinity. Beautiful answer. Now, before we walk away from this example, I just want to show you why it's true that an entire region keeps it positive or negative or something like that. So what I'm going to do is graph this quadratic equation, 6x squared plus x minus 2. And when I graph that, you see it's a parabola. And in fact, maybe I'll zoom in a little bit. I'll make my window go from, like, let's say a negative 5 to a positive 5 in the x direction. That might be a little bit easier to see. Okay. What we're asking is, when is this parabola above the x-axis? In other words, when are my y values greater than or equal to 0? So you see, once I get beyond or above the y-axis here, I'm always positive. So anything to the left of this x-intercept is always positive. Anything to the right of this other x-intercept is always positive. Anything in between the x-intercepts is always below. And that's exactly what we've represented in our graph right here. We've basically just turned on the light above this graph and shown the shadow of what's positive down onto the x-axis. It's a really good way to think about it. Let's do one more and then we'll call it quits. In this last example, what we're going to do is solve the inequality -3 minus m squared is less than 0. And because I hate having negatives on my variables, my lead variable terms, I'm going to move everything to the other side of this equation. In other words, I'm going to add m squared to both sides, and I'm going to add a 3 to both sides. If I do that, I'll get this. So I really want to know, when is m squared plus 3 positive? That's what that's asking. When is m squared plus 3 positive? I don't want it to equal 0. I want it to be positive. So we first start by trying to solve m squared plus 3 is equal to 0. And when you try to solve this, something strange happens. I'll subtract 3 from both sides. And now to unlock m from being squared, I take the square root of both sides. Remember the square root property: if m squared is equal to a number, then m is equal to plus or minus the square root of that number. And we have an issue. That is an imaginary number. Well, that's imaginary numbers by themselves aren't horrible things, actually. But I know that I'm trying to graph this number on the number line. And as far as I know, the number line only contains real numbers, not imaginary numbers. So there's no point on this number line that will satisfy m equals plus or even a minus the square root of a -3. There's no such point I can plot here. So when I go to pick a test point, essentially I can pick any point I want, because all the points on this number line will share the same quality for this quadratic inequality. So an easy point to pick would be m equals 0. We'll just pick that point. If you let m equal 0, plug that into your inequality here, you'll get 0 squared plus 3. Well, that's always positive, isn't it? So that means that everything, no matter what I plug in for m, this inequality, or this side of the inequality, the right hand side of the inequality, will always be positive. And you could try it out. Plug in m equals -10. -10 squared is 100 plus 3 is 103. That's still positive. So it doesn't matter what I plug in, my equation will always be positive. M squared, or actually my expression, m squared plus 3, will always be positive. So the answer to this is everything makes this true. In other words, this whole number line, let me just shade that in just to kind of show you. This whole number line here makes the inequality true. So how do you denote that? Well, it goes down all the way down to -infinity, and it climbs all the way up to +infinity. These are just concepts, so you cannot ever touch them, and that is the solution set. You can plug in anything you want. And you can try it out, actually. Like I said, just try plugging in any numbers you want in for m, and you'll find out that this inequality is always true. So I guess that rule of thumb, when you try to solve a quadratic inequality, move everything to one side, which we did here. Then say, let it equal to 0, and try to solve that, and plot those solutions on the number line. All that still holds. But if you can't plot solutions on the number line, you still have to make a sign chart. You don't have 2 regions or 3 regions to test, only the one. And if your expression is positive in that region, in that one region like this is, then it's always positive. If it was negative when we tested it, it would always have been negative.